with lecture 13. I'll continue with stochastic differential equations. This is probably the last session on stochastic process, on pure stochastic process, or the previous to last, so I'm almost done with this mathematical part. Today I will discuss what I have in the slide. First, I'll do a reminder of the Fokker-Planck equation, which I gave you yesterday, and what is the probability current in a Fokker-Planck equation, and what is the stationary distribution with some examples. Then, okay, please go back. Go back. Can you go back to the slide? Sorry, who was sharing?
I was sharing just a minute.
Okay, just don't touch anything, just share that slide, okay?
I am, yeah, okay. Yes.
Just a slide. Perfect. Don't touch. Good.
Okay.
Thanks. Then I will discuss the Langevin equation, which it is a very celebrated equation in statistical physics, and it is also it could be the motivation of all this story on stochastic differential equations, and you will see why. This is a very important equation in physics. Next, I will share with you a particular example of a Langevin equation, which is the Austin-Uhlenbeck process, also very important in physics. And finally, I'll do some remarks about the Ito and Stratonovich calculus, because until now, I tell you, I'm talking about stochastic calculus, but I'm only talking about one type of calculus, which is called the Ito calculus. Then there's something else, other types of conventions to make integrals and to make derivatives with the stochastic process. And one of the most popular ones is Stratonovich, which I will discuss at the end of my lecture if I have time. So now I go to Blackboard, and I hope, I think you don't need to share screen. That's it. You see me? All good?
Yes.
Fine. Thank you. So I go with lecture 13. Which will be on Fokker-Planck equation with the probability current. And also on the Langevin equation. And Austin-Uhlenbeck, and also Ito versus Stratonovich. So each of them could be one entire lecture, so I'm going to be brief. So please ask me if you have any questions during my talk, during my lecture. So first of all, I'll start with a reminder on the Fokker-Planck equation from yesterday. In which we'll say that we have following stochastic differential equation. T plus G60 dB. Right? For this equation, the associated Fokker-Planck equation for the probability distribution is following. Time derivative equals minus partial with respect to x of f t plus 1/2 second derivative of g squared pxt. this is what we showed yesterday. We had a mathematical proof for this equation, and you will meet this equation in different fields. You will see it later in your course or in your career. So
I
now,
have a question.
yes.
So we did Markov processes earlier, and we had probability currents in that as well.
Yes. Yes.
Is this for the continuous case?
Yes, exactly. So this I'll talk to you about it later. So before you had discrete Markov process. So you had something like this, for example. No? Okay. Imagine you have a Markov chain in continuous time, and you have these transitions. And you could do master equation for the probability of every state. So you could say pi dot equals, you remember, no? There are the rates. For example, p1 dot in state 1 is in state 2. So w1 to p2 minus w from 1 to 3 p1, for example, no?
Yeah.
And then you could define the probability current anywhere. For example, here you could say j 221 was p2 w12 minus p1 w21. All right, this was in the discrete world. But now we are thinking about continuous. Okay, continuous would be that instead of having this square, you would have, for example, a circle. You will have a space in which you have, okay, instead of 4 states, they are infinite. X is a real variable. Okay, this is like taking the continuum limit. Instead of having 4 states, you have stay here, 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 here. You have infinite. Okay, x could be the angle here. This could be x. Okay, and in this world, we will calculate the current, so the probability to be in this position in the ring, and the current flowing through a given position in the ring. This is more or less the connection.
Okay.
You can think about it also if you consider another Markov process, which could be in the open space, could be the random walk. So you have a system that has state 0, state 1, 2, 3, sorry, minus 1, minus 2, and you have a walker that's jumping. Okay? The walker jumps between discrete states, and you can, for example, you can put more probability to go right than to go left. This would be P, and this would be Q, for example. This would be the bias on the walk, and you could say, for example, P is greater than Q. Okay, with P plus Q equals to 1. In this case, you could compute the current through, for example, here, which is the same as the current through here, because this is a line. Okay. This, when you consider many states, it will be transformed into a diffusion in the x-axis, in which you have a particle that can move and can be in infinite positions. So the equation for this motion, instead of P and Q, you will have something like this. Px will be infinity plus square root of 2d noise. Okay. This will be a drifted Brownian particle on the real line. So this can be obtained as a limit. From here to here, you can do the continuum limit. This is Markov jump. This is continuous. Okay, this is the class of the process, but the name of this process is bias random walk. Bias random walk. And this one is the biased diffusion. Okay, but taking the continuum limit, you can go from the Fokker, master equation to the Fokker plan. We didn't do it here, but okay, we could do, for example, on the next class. Okay, I'll show you how to do the mapping. Now we live in this world. There is a continuous space, and our system has fluctuations and moves in a real line. So the equation of motion, sorry, the equation for the probability density is this one. Okay, now let me write here. It was a panel discussion. This is a good point. I think in the next class I'll show you how to do the limit. Alright, so we have this equation, and what we can do now is to write this part as follows. Partial with respect to x of fxt dxt minus 1/2 partial with respect to x of t squared t dxt. Okay, again, now the only thing I did was I pull out the derivative, right? Nothing else than that. And this quantity that you see in the brackets is what is called the probability current. This is called the xt, time-dependent current. Time-dependent, space-dependent current in general. Partial with respect to x with a minus equals partial with respect to t of txt. Okay? This is the same as saying Fokker-Planck equation. Right? For this, as I said, is called the probability current. Right? So remember, I think I do here a bracket because this is just a reminder of, for instance, in electromagnetism, there's a divergence theorem, and you can say this is in electromagnetism. You may think, I don't know if you remember, the divergence theorem, all the Maxwell's equations. So there was this equation, this for the charge density plus the divergence of the flux equals sigma. This was a production term. So in general this is written in 3D in electromagnetism, but we can also write this like 1D, like this. Equals sigma. And remember that this was the rate of change of the charge density. This was the charge density. Charge density. This is the divergence of the flux. And this is the production production. I don't know if you remember this type of equations in electromagnetism or if it's in physics, but you have a volume of with charge, and the charge can change in a given volume by flowing out of a surface. This was what this term was giving, or by being produced inside of the system. This you have to take the books and go back, but this is just to tell you that the equation that we get now for the probability current, has the same structure, but now there is no production term. It means that there is no creation or destruction of probability. Okay? This happens when you have something diffusing on a line or on a ring or somewhere where there is no death of probability. If we had a system where there is an absorbing boundary, so I diffuse and there is a trap, and when I arrive to the trap and I die, there will be a production term. Okay? For example, if you have particle diffusing in a line, and there is here a wall, and when the particle reaches the wall, it is evaporated. In that case, there is a destruction term. We are not considering this here. That's why we have partial T of P is minus partial x of j, plus there is nothing else. Okay? There should be something else if there is a production of probability, or a destruction of probability, like when there is a hole. But we are not considering this right now. Right? So, very good. So now, with this, let me just tell you that this is time dependent. So of course one can define the stationary quantities. Remember, stationary was meaning time goes to infinity. So for example, P stationary x is the limit when t goes to infinity of P xt. And you can have also the stationary current, which is the limit when t goes to infinity of the xt. This is the way we define them. And now I can think about how you get the stationary distribution. So if you come to this equation, stationary means it doesn't change in time. So stationary means that partial t of this partial t of p equals to 0 in the stationary. This is stationary limit is this. There are no changes in time anymore. This means that one can get from this equation the stationary distribution, because this implies that we have minus partial x g stationary x equals to 0. That means that the stationary current has no divergence, or it has no, we can write it like this. Okay. And secondly, it implies that we can get from this equation the stationary probability. So when t goes to infinity, this doesn't change. This is 0. So it means all this equals to 0. So it means that we can get from here the stationary distribution. Stationary distribution obeys this equation. Partial x of f x. Well, let's say, forget about t for a moment. Dx minus 1/2 partial x g square x dx, st equals to 0. So this is in general a difficult equation to solve. So if you want to solve the stationary state, it will be complicated in general. Okay? So what does this result mean? For example, if we have this example, it will be very paradigmatic. Imagine we have something like this. We have a ring. We have a particle in a ring. And let's say the particle has a drift V and has a diffusion D. So the equation is something like this. V dt. This would be, if there is no noise, dx is V dt. But now we say there is noise. Sorry, dt. Which has amplitude 2d. So this would be the equation. We could say, for example, that x of times 0 is 0. And we could also say that x is in a ring. So x of t belongs to, for example, 0 to 2 pi. Okay. So when you have this equation, you realize that one thing. In the stationary limit, we are in 1D, we are in closed environment. We have partial g x equal to 0. So it means in 1D, okay, be careful, this is in 1D. It means that the stationary current is constant, J. So it's independent on x. Wherever we look, there will be the same current. Okay? And now what you can do also is to try to see what is the value of the current in this example. So you can come to the definition and say, okay, the current reality will be something like this. F times P. Okay, let's do the stationary current. This is T. F times P. F now is this one. This F. And this is for us G. Okay? We write like dx is f dt plus g dt. So you come here and this F is V. This is P stationary. And then the next term is minus 1/2 partial x g squared P. So minus 1/2 partial x. And then g square is the square of 2d. Yes. And now it turns out that PST is independent. The ring is homogeneous. So in the long time limit, if you put many particles in 0, you let them go. If you take a photograph at long times, you will see the ring is uniformly distributed. So PST doesn't depend on x. This means that this term is 0, because D doesn't depend on x, and P stays in the stationary limit doesn't depend on x. So this would go, and you just get D times PST. So you see, in this case, the stationary probability is what you expect, V times P. But in general, it will be more complicated. It will be, the noise will have contribution. Right. So maybe to give you a better insight, you can try to give you an intuitive idea on what is this J, the current. Remember, in the end, what I'm telling you is just that the current is what comes from the right-hand side of the Fokker Planck without the derivative. That's what I'm saying. Yeah? That is useful because later, if we do models of molecular motors or of polymers, this J will be related to the speed at which a motor is growing, at which a polymer is growing, or the speed in which a motor is moving. So it will be relevant for different biological systems. Okay, now to give you a picture of what I'm talking about, you can say that imagine this is x, and this would be, this would be p of x time t. So at a given time, I plot the distribution of x. Imagine it has this Gaussian shape. Now I'd like to know what is the probability that extra time t is in the interval x0 plus delta x. This is a small interval. I would say from here x0 and maybe it's better if I am a bit more exaggerated, like this, for example. And this is x0 plus delta x. What is the probability to be in this way? So, what do you think it will be? Imagine I give you this. So, what is the probability given that you know this curve? Exactly, it's the integral. It's the integral of the density. A probability has no units. Probability will be 1/3, 2/5, 2/5, 1/2, etc. But what I'm writing is pxt. This has units. This is a density. Okay, probability density. Remember that pxt dx equals to 1. When you have something like this, it means this has units of length, this one, and this, because this has no units, this must have units. It has units of 1 over x. It is a density. Therefore, as your colleague is saying, this should be the area under this curve. It will be the integral, in reality, the integral between x0 and x0. Is the integral between x0 and x0 plus delta x of t x t dx. That's the definition. Okay. But now I'll say that delta x is small. Say delta x is small. So when delta x is small, we can approximate this by the value at x0 and t times delta x. This is a bit of a crude approximation, but it's like making this rectangle, okay? When delta x is small, this is a good approximation. You see, this is the height, and this is the width of the interval. Nothing less than that. So now, I would think about the following. Think about what is the rate of change of this probability as a function of time. How much does this probability change? And this we can rationalize as follows. So the change that happens here is due to the following. So it's due to, you can think about like the fall of this curve as, or the change of this curve as a balance of flow. So there will be flow of probability entering this region and a flow of probability getting out of this region. And this in the book I'm following, which is the one I recommend you to look, can be seen like this. There is a flowing of value r x0 t. These are the number of particles that are flowing from this region, all this region, to this area at time t, per unit of time. This is why I call it r. And then there will be a flow out from here. Flow out at a rate x0 plus delta x. Okay, they are getting out from x0 plus delta x. Here they are getting in x0. So then we can say the rate. This is all. I'm not doing this mathematically very detailed, but this is to give you an intuitive idea. Okay, for the mathematical derivation is what I did yesterday. So the rate of change of this probability is P x0 P delta x is the difference between the probability flowing into the interval minus the probability flowing out of it. So we would say something like this. P x0 P delta x. This is the rate of change of the probability. Will be how much we get in T minus how much it does go out. X. And now what I'll do is I will divide by delta x and take delta x going to 0. So if I divide by delta x, it goes, and I just have the density. And here I'll have the limit with a minus. It's a minus here. When delta x is to 0, I put a minus to put first this one. 0 plus delta x, P minus R 0. P divided by delta x. And this is what I call the current. This in this limit is something like minus partial with respect to 0 of R x0 t. So then this implies this is the same type of equation I showed before. This implies, in few words, sorry. Remember, all I'm doing is in 1D, but this can be generalized to different more dimensions. So this implies that what we understand or call JXT, the current, is the rate of probability flow at time t across the point X. And remember, very important, that we are writing the equation like this. Okay, this is a very lazy way to write it. Remember, I'm talking about pxt, partial derivative of t pxt, but in some courses, in some lecture notes, in whatever, we will find something like this, okay? But think that p has depends on two quantities, x and t, okay? And it is a density, think this. And also there is an initial condition. So I am putting under the carpet a lot of things when I write it like this. Eh? What I want you is to understand. You understand what you write. You understand that this has dimensions of 1 over x. This is very important. But in reality, this p in reality is p xt given x0, 0, right? There is an initial condition that you give to the process. Okay? First I put this under the rug, But then now I'm putting all this. Okay. But remember this, eh? Remember this. Percentage of P equals minus partial x of j. This is what you have to understand. If you know the Fokker-Planck, you know what is j, because it's immediate. I show you in 2 minutes. But now remember that this has units of 1 over x. So the units of P is 1 over length. L means length, so it's 1 over, no, meters minus 1, or meters minus 1. So the units of j is 1 over t. It's obvious, no? Partial tp, so it will be units of 1 over xt. And here partial xj will be units of 1 over x and 1 over t. That's all you need to understand. J is not a velocity, because it doesn't have units of velocity. And in some examples it's a velocity. I show you one example. In the particle in the ring, J is a velocity. It's just the velocity of the model. In general, it is different. It is not a velocity. Okay, I hope this is more or less clear. If not, please let me know. Because the next thing I want to introduce to you is a very important equation in physics that I also use a lot for research, which is the Langevin equation. But I think I'll do a short break. Maybe give me a second. Okay, any question or doubt? This was just very, very simple. This was just to define the current. But what I will introduce you now, it's a given. The Langevin equation is one stochastic differential equation that it's very famous in physics, and you should all know it and dominate it. Yes.
I have a question.
Yes.
So when we're talking about stationary processes, what I understand is that across time, the probability distribution will not change. Is that right?
Sure. So you can think, for example, the problem of the ring is 1. So
distribution
doesn't change in time anymore.
If it doesn't change in time, then we can't predict anything. So if we're looking at a process and if there's something that we would like to predict because the mean and the variance won't change, am I on the right track or am I not understanding this right?
Wait. Let me give you an example, and I think this will be clarifying for you. Okay. So imagine, and this will be related to what I will explain you in the next part of the lecture. Imagine you have a potential. This potential, okay? It's a parabola. Parabolic potential. V of x equals 1/2 kappa squared. Okay, the potential at x0, this is 0. This is V of x. This one. Okay? It's a parabola. Imagine I take a particle and I am initially here. The particle, the initial position, x0, equals to -1, for example. Okay. So what will be the distribution at time 0? The particle has this initial condition. So where will be the particle at time 0? Here, no? Here. So the distribution, this is x, and this will be p of x and p of xt. At time 0, I will be sitting here. So the distribution will be in -1, it will be picked. It will be a delta. This is p x at time 0, which is delta of x plus 1. Okay? You agree?
Yes.
Then I will let the system evolve in time. So this distribution will change. This was the distribution at time 0, and what you will see is a diffusion of the distribution. The distribution will start doing, for example, a short time will be like this distribution. Okay? It will spread a little bit.
Okay.
Because if you think about many particles, one particle could be here in a short time, another will be here, other will be here. Okay? You have to think about an ensemble. The ensemble of particles will have this distribution.
Okay.
So P of xt is changing. You see, like, okay, there is a change in time of the distribution. But that is changing in x, because before there was nothing at this point, but now there are.
Yeah.
So the distribution will change, will do something, and the stationary distribution is what happens at infinite time.
Oh, okay.
Where are the particles at time infinity? And I ask you, what do you think it will be? Where the particles will be near zero, no? The particles will fall.
Yes.
So PST of x will be, this example is easy. You don't need to do complicated math.
Yeah.
This
It
example,
must be delta of x then, because there's no zero, right?
no,
It's
no,
at zero.
be very careful
No.
with this. The particles won't come to zero and stop. They will continue moving. Now we are not in an ideal world where we are in vacuum. We are in a thermal bath. The particles continue moving. So, okay, there will be particles here at long times, others here, other here, other here. There will be, for sure.
Would it be delta of x plus, let's say,
No,
delta x, which is like a small
no,
change?
no,
From
no
zero?
delta, no delta, no delta. Delta means all the particles are in one place. Be careful.
I'm sorry, I lost the connection for a minute.
Okay, no delta,
Yeah.
because,
Why?
no, think about it. At time zero, I say my initial condition is to be in -1. In that case, the distribution is a delta because all the particles, if I think about an ensemble, all of them are placed in one position.
Okay.
Now they evolve. Some of them
Also,
go,
it'll be, okay, it'll go to Gaussian then.
yes, but why Gaussian?
Yes. I'm sorry?
Okay, why it goes to Gaussian?
Because it disperses.
Sure, but not always goes to Gaussian. And look, I show you now. It will go to Boltzmann distribution because this goes to equilibrium. So it will be e to the minus beta v divided by z. Okay, z is a constant. Okay, but v is a parabola. Okay, so if we put this formula here, we have a parabola. This will be v kappa x squared divided by 2. Gaussian. You're right. But be careful. Be very, very careful. You cannot say like this Gaussian, because what if now I give you another potential? So I will give you, for example, this potential.
It depends on the potential.
No Gaussian. No.
It depends on the potential.
Yes,
So-
because imagine I give you this. A x2 plus b x4. This is called the double well potential. There are two wells. So now, be very careful with this, because the fluctuations are Gaussian. But you can go to a state that is non-Gaussian. In this case, in equilibrium, I recall equilibrium, so there are no other forces, just the diffusion. You will have beta v of x, and this will be e to the minus beta, this thing, a x2 plus b x4, divided by z. This is a very good question you ask me. But it's very good that you guys and girls realize, not always you will go to Gaussian.
Okay.
The Boltzmann, people, when they talk about Boltzmann distribution, they almost always tell you about the harmonic potential, the parabola.
Yeah.
But not everything in life is a harmonic potential.
Okay.
Okay? You can have a double well. It is a very, very natural situation in physics when you have oscillations, for example. So be very careful about this.
Thank you.
Boltzmann.
My question.
Huh?
My question was that, So it's stationary. When we're talking about stationarity,
Stationarity means
we went from from the initial condition, it's still the distribution still changed.
yes, the distribution was changing, but there's a time in which it doesn't change anymore. The distribution. At long times, this distribution will be like this will be two peaks like this, and will stay like this forever.
Okay.
Forever means in the long time limit.
And for every process, obviously that time limit will be different.
Yes, exactly.
The time scale will be.
The time scale will be different. I change the potential. Imagine if I put like a triangle, then it won't be a Gaussian. But in the long time limit, there will be one distribution, and this will be the so-called stationary distribution.
Okay, thank you.
I think that's clear, but this is a very good question because I think without an example, it's not obvious to get this point. Okay, very important. Okay, I do another box here. I should do the break, but this is important, which is in equilibrium. Well, I will go to this later. The stationary distribution is Boltzmann, but in non-equilibrium, this is called NES, non-equilibrium stationary state. dx is not. It is not E minus beta Vx divided by theta. Okay? Here I'm saying it's an equilibrium. So it's a particle that fluctuates. It is in a bath at temperature T, and there is no one pushing the potential or changing or anything. It is fixed. It is equilibrium. But one can think about non-equilibrium steady state, which is another situation in which you cannot say this. Okay?
Okay. And yes, we discussed that stationary and equilibrium. We did this before as well. Yes.
Sure. But now when I explain you Langevin, you will see more clear, I think.
Okay.
Alright, so I had to do a break, otherwise I don't get oxygen. So please, let's do 5 minutes break and we continue. Okay? Stationary state. Yeah? Be careful with this. A common mistake of people. Common mistake. Right. So the next part is related to this. There is the Langevin equation. It's what I introduce here. I'll discuss this part. The Langevin equation. If I get my notes correct. The Langevin equation. Well, anyone knows who was Langevin? Some stories, something? There are many important characters that appear in ethos, I don't know which, Langevin. No, you didn't see a movie on Marie Curie recently? You should watch it, it's very nice. And Langevin was a French physicist who was investigating different topics. One of them was Brownian motion, and he came up with a very interesting phenomenological equation. So it's not an equation he derived, it's an equation he postulated around 100 years ago. So it's from 1908. Back then Einstein was doing also his theory about Brownian motion. Remember, the theory from Einstein is 905. This is 908, so it's very close in time. And the model Langevin was thinking about was small system. For example, could be a Brownian particle, colloid, which is immersed in water. So water, as I said, there are molecules here, interacting with this colloid. We call it this colloid, which is of the size of a micron, for example. This is the typical size of bacteria, we said, different objects in biophysics. And he was thinking about colloid that has a mass m. This would be the mass of the colloid. Mass of the colloid. It is assumed to be much greater than the mass of the water molecules. Okay? At least for my first part of the lectures, you could realize that it is. This is like 1 picogram. And this is much, much less. 10 to the minus 27 grams, the mass of a water molecule. Second, another ingredient of this theory is that, okay, this is a mass, and this object has a velocity, no? So one could think about the velocity. Well, let's do the theory in 1D, but one can do it in many dimensions. And the fluid opposes resistance to the motion of the colloid with a friction coefficient, which I call it gamma. This is the friction coefficient that results from the fluid opposing the motion of the colloid. Right? What else do we have? We have also that the bath of water molecules is a thermal bath. So we say the water molecules are in equilibrium always. There is a temperature here. This is the temperature of the bath. Okay, what else? So the colloid is not just moving freely, but there can be potentials, as what I told you about here. And there could be also external forces.
No?
Sorry?
There will be fluctuations because it's moving around.
Sure. The fluctuations are because we have the tip here, okay? This is fluctuating, so this will move, the center of mass will be going like this, okay? There are fluctuations. This is taken into account by this and this. Okay? But apart from fluctuations, there is a potential, there can be a potential. There is a force, F of X. This will be the force exerted on the colloid. Force exerted on the colloid. And something very important for you is to realize that forces can be two types of forces. And maybe some of you can guess which type of forces I will talk about. Maybe not. Okay. One is the force that comes.
Conservative?
Sure, conservative and non-conservative. So conservative is the force that derives from a potential. So we say F of X will be on one side minus B prime of X. This will be the conservative force. Conservative. This comes from a potential. But secondly, there could be non-conservative forces. Forces that do not come from a potential. This is this small f. Well, maybe small f is not good, because this is, I used it before for something else. But let me just call it F NC of X. This does not come from a potential. Okay? So you could have a force not coming from a potential. For instance, there could be that a force acting on a particle here that doesn't come from this potential. There is the potential, there is something else. There is an agent that is doing something on the particle that is not captured by the potential. That is what is called the non-conservative. For instance, you could have, let's think about a ring, but now in the ring there is a potential, so it's like a roller coaster, okay? If you have a roller coaster, it's something like this, okay? So I'm not drawing very good, but this is to tell you that there is a roller coaster in which a particle is diffusing, so it can fall here, it can fall this way, the roller coaster, and this will be a potential. The roller coaster is fixed, But then on top of the roller coaster, there is a torque. So there is someone who is putting a velocity, net velocity. So there is a force like this, let me call it F0. And then on top of that, there is this roller coaster potential. In that case, when F0, okay, there is F0, and there is V of x. So this means, okay, here x will be the angle. This means that the total force will be minus V prime x plus F0. When you have this force, you don't go in the stationary state to both one. So, for example, if you take V of x equals sine x, then the stationary distribution, it is not e to the minus beta sine x. Okay, just by adding this external force, you get out of the Boltzmann. Okay, so this is the non-conservative part. Which means that if it is different to 0, we have non-Boltzmann. Non-Boltzmann stationary state. If it is different to 0, right? Remember this. Okay, so this was a bit, I was diverting a bit from the ideas of Langevin. So these are the key concepts, the key parameters of the equation. And now the equation, what it does is it gives a phenomenological equation for the motion of the core. So equation is what I'm trying to, I'll try to write it here in detail. But you will see it is very intuitive and very physical when I write it. It has two forms. One is called underdamp and the other is overdamp. And you'll see what I mean about this. So, alright. The equation is as follows. We will say the mass of the particle times its acceleration. Okay, remember x dot dot is two derivatives with respect to time, so acceleration. Okay, so I will apply a kind of a Newton law. So Newton's law will be mass times acceleration equals forces, no? Sum of the forces. That's the second Newton's law. So you write it m of x dot dot equals the sum of the forces. Okay? This is the philosophy behind. And now I'll tell you which are the forces coming here. So let's go one by one. Who can tell me one of the forces entering here? Okay, let's go one by one. So the mass appeared. Fine, I'm happy. The friction. What is the force done due to the friction if I assume I'm in low Reynolds number? I have to go back to my lectures at the beginning. The friction force. How is the friction force? When an object falls, what is the friction of the fluid to oppose the falling of the object?
The proportional to the velocity.
It's proportional to the velocity. Here is the proportional to the velocity, to the instantaneous velocity. We'll have this minus gamma times the velocity. This is the friction force. Okay? The first one. This is friction force. Minus gamma is dot. What else? Okay, so I use this. Let me leave this for the end. What else do I have? The forces, no?
Yeah.
This is another force. It's the forces from the potential or from an external agent, effect. This is forces. So forces from potential and or external agent. Okay, and what else? Okay, so I also took care of this. There is a path, no?
Yeah.
These water molecules are colliding with the colloid. What type of force do they give to the colloid? Is it f of x, or is it... What type of force? So, one water molecule comes at time 0, then another one comes at time 1 nanosecond, then another one comes at time, I don't know, 30 nanoseconds. What is the nature of this force? So what did we learn in my last 3 or 4 lectures? What type of new forces did you learn? Brownian force is a noisy force. I told you, noise. There is also noise. There are all these forces, the friction, there is the force from a potential, but then from time to time, one of these guys comes and kicks the particle. That's a noisy force. Noisy force, okay? So that's the noise. And which noise we will put? We will put the white noise. Okay, so what we done was the following. There will be an amplitude of the noise. So if I put just psi, the noise we learn, the white noise, psi has amplitude 1. So we need a force that has amplitude related to the temperature. If there is hot temperature, the water molecules will be moving very fast and they will give strong forces. So we need a force proportional to the temperature. The way it comes is like this. 2 mt gamma times noise. This is the noise. This is the thermal noise. Okay? So it makes all sense. There is the acceleration of the particle. This is the inertia, we could call it. The inertia. There's a kind of a Newton law with different terms. Friction, forces from the potential or external agents, and thermal noise. Okay, so this is the Langevin equation, if you remember. It's important, physics. It is called sometimes the underdamped Langevin equation. Right? Langevin equation. Okay, I must say something about the noise. The noise is a white noise. It's a Gaussian white noise. So psi t is a Gaussian white noise. Which means, and you should know, the distribution is Gaussian, the average is 0 at any time, and the autocorrelation is a delta. This comes from my previous lecture. Okay? Follow me? Any doubt? Any question? No? Right. So this is very important equation in physics, as I said. But most often, many times, we neglect this term. Often we neglect this term. So it's like a Newton law, but with zero acceleration. Often that's what we do in physics. and this is what is called the overdamp limit. So this is underdamp, but we can also take the overdamp limit, in which the mass is also small. Mass small means that this term is smaller than any of the others. Okay? So this is the overdamp. Overdamp algebraic equation. It will be taking n small. Or you can also find this limit. This is very interesting. If you have, okay, here I'm in one dimension, but you can do this in 2 dimensions as well. And if you solve this equation, you have like a Brownian trajectory that is kind of smooth like this. But typically, you have finite time resolution, so you can only sample, or you can have a camera, so it has a frame rate, so you cannot see the system at all times. That's not possible to do in an experiment. So typically, you sample in between discrete times, like this. You sample this trajectory, and what you get is a more rough trajectory that makes like this, which looks more like what Brown was seeing in his microscope. Okay, something more rough. This will be also the overdamp limit, in which what you do is you look at finite delta t's in a way that they are bigger than the mass divided by the friction. This is, you get the same result than what I'm going to show. So you get also Brownian trajectories in which you remove this term. This is very, very small. So you just get with that. And now what you do is this is with a negative sign, so you move it to the left. And you are left out with this equation, which is f of x plus square root of 2 kBt gamma noise. This is the so-called overdamp algebra equation. So very important. And now this should do a connection with the lectures that I was telling you until now. Because we have x dot equals force plus noise. So we can divide by gamma and multiply by dt. Remember, x dot is dx dt. So if we multiply by dt, we will have here dx. Here will be a dt, and here will be psi dt, which is dv, if you remember well. Okay? And if I divide by gamma, so I will call mu to 1 divided by gamma, this is called mobility. And if gamma comes down here, this becomes 2 kBt gamma divided by gamma squared. It becomes 2 kBt divided by gamma, and that's d. It's 2d. So I would use also the Einstein relation, d equals 1 over, kBt over gamma. This is from Einstein. To get, I can write it like this. So these two, I use these two equations to get either in this way, x dot equals fx plus, so mu fx plus the square root of 2d noise. This is one way of writing it. Okay, mu fx plus square root of 2d noise. This is also the Roldan equation. But now be careful, because this was a force balance equation, and this is an equation for the velocity. It's a dynamical equation, stochastic. But you can write this again as dx equals mu fx dt plus square root of 2d dB. So now we enter in the world in which I explained the previous lectures. So this is totally connected to my previous 3 lectures. the Langevin equation becomes something we can treat. Now we can use our tools and get the probability current, the Fokker Planck, whatever, for any model of Langevin equations. Okay, I hope this was clear to you, more or less. Okay. One example is very famous of the Langevin equation. It is called the Austin-Uhlenbeck process. I'll finish my lecture with this. So I leave it on note for the last lecture on this block, which will be next Tuesday or Wednesday, I don't remember now, to check. So this is the Langevin equation, but one particular case is when we take the force from a parabolic potential. That's what I was telling you before. That's called the Austin-Uhlenbeck process. It's a bit complicated to write, but you should get used to it. It's Ornstein-Uhlenbeck process, or OU process. It is an overdamped Langevin equation. So it is following overdamped Langevin equation in a parabolic potential. I never remember if parabolic has one L or two. I think it's one. Just correct me if I'm wrong. Potential, for example, P of x equals 1/2 kappa x squared. For example, okay. For this, the force, I say there's no conservative forces, so all the forces are conservative. So f of x is, what is f of x? Nobody knows.
Negative kx.
Negative kx. If you do the derivative with respect to x, you get kx, but you need a minus sign, so it's minus kx. Kappa x. This is a spring, okay? This is a spring. Minus kx is a spring. It's Hooke's law. So you have the potential. The potential is 1/2 kappa x squared. So you are here, the force is very strong. You're here is weaker. You're here, the force is 0. So this is like having a spring with a mass. Well, it's a 0 mass, but you have a system in a spring with noise. So the equation is like that. So it's gamma x dot equals minus kappa x plus square root of 2 kb gamma. This is the Austin-Uhlenbeck process. You made this equation. The Austin-Uhlenbeck process has a lot of nice properties. That is one of the few Markovian processes that has a Gaussian limiting distribution. One of the few. But the nice thing is you can also simplify this and write it, for example, you can see it written in different ways. So give me a second. How can you? It can also be written like that. I divide by gamma, and you see this will be x dot, there will be x. So if I have x dot here, there should be something like x dot. It will be x divided by tau. This will be a relaxation time. plus divided by gamma, we have 2D noise. Okay, where tau, when we call it tau r, is the relaxation time. It's gamma divided by kappa, it's 30 units of time. It's called relaxation time. And something very nice you can realize is that we can make an average here. We take an average, this is fluctuating, this is fluctuating. This is also fluctuating but has average 0. So if I take averages, I get gamma. Or let me come here. X dot equals minus x divided by tau r plus the square root of 2D average xi. What is average xi? Average of the binary process? Sorry, of the white noise? 0. 0 average, so you just get this. It's a very simple equation for the average. X dot equals minus something x, so the solution of this is an exponential. But even more, what I can tell you is this is one of the few processes, one of the few stochastic processes which we can solve exactly. We can get a solution, analytical solution, and we can do it as follows. Okay, maybe close to the end of the lecture. So how can we solve the equation? This usually is not possible, so it's a very special equation. How can we solve this equation? So you have learned about ODEs, no? And you know how to solve x dot equals minus x, for example, no? You know how to solve this. You also know how to solve this, no? Which is this part. And you also know how to solve, you know, this, right? It's a time-dependent quantity. It's a time-dependent. Okay, now it will be stochastic, but it's a time-dependent quantity. So it will be of this type. So if you solve this equation, just you are blind that is stochastic, you just try to solve it. You have this minus, I think it's t over a, no? Or it's minus 80. Minus 80. Minus 80 plus e minus 80 integral 0 t e a s hs ds. I think it's called Leibniz formula, if I remember well. Okay, this is the solution. But now the story is what is A and what is H. So H will be all this, which will be a fluctuating quantity. So in this problem, we get x of t will be x of 0, e minus t over tau r, plus, I can write it like this, 0, well, maybe I write it simpler, minus t over tau r, integral 0 to t, e s over tau r, and now it comes this, which is a time-dependent quantity, will enter there, square root 2 gamma times psi of s ds. So you see that now when we solve it, there is a random increments. So this, we said before, this is dV. So there is, when you solve it, you see there is a part that is deterministic, and there is a part that is stochastic. That's the solution of the problem. You could solve it in different ways. One is doing a numerical integration of this equation, and another would be to do this, but at the end you will need to sample the noise. So each sample of the noise will give you a different trajectory. You see it here. You see it here. In the next lecture I will go into a little bit more complicated case in which here I'm doing integral of dvs, but all this is deterministic. It will be much more challenging if I have dvs and here something noisy. That's called stochastic integral, and I will dedicate some time in my next lecture to it. But by now, you can see I can get this again, because if I average this, there's only this to average, x0, if I start from a distribution. If x0 is given, there is an average of a delta, so it will be just x0. This is not stochastic, not stochastic, not stochastic. This is the only thing stochastic here. But this is equal to 0. So I get x of t average x0 e minus t divided by gamma. An exponential. Just an exponential. As it should be. Because the average of x should go to 0. If you take the limit t to infinity, this goes to 0. Okay, this goes to 0. Sorry, this goes to 0 when t goes to infinity. The average goes to 0, not the variance. Not the variance, eh? It means we put many particles. Let's say I go back to the problem I told you before in my lecture. So we have a potential, and imagine I put many independent particles here at time 0, and I let them go, let them go, let them go. So at the final time there will be a distribution like this, but the average would be at 0. This is what this equation is telling us. This is what this equation is telling us. And I don't know if I have time, but I could also show you the usefulness of Ito's lemma here. Okay, do you give me 5 minutes? Okay, just one more thing, which is here you can see that Ito's lemma is useful. This for this example. So I calculated here the average of x at long times, but I'd like to know also what is the fluctuations when t goes to infinity. What is this? So of course I could solve the distribution, get that this is a Gaussian, and know that the variance of the Gaussian is kBt divided by kappa. This I could get it directly, because I know the final distribution is a Gaussian. I could get the variance from it. But look at the following nice trick. X squared. So we can do a change of variable, use Ito's lemma, Ito calculus, and say, we define a variable y, which is x squared. What I told you in one of my previous lectures. So then I apply Ito's lemma, so dy is 2x dx plus g squared dt. Just revise my previous lectures and you will find this. So there is this part, which is what you expect from calculus, and there is the second derivative with dt. Okay, so now what you see is that what I can do is I put whatever is dx, I put the equation, so I have dy is 2x, and then dx is minus x over tau dt plus somewhere here, square root of 2d db plus g square root is 2d dt. Okay. So now you see it, because if I want to know d dt, how much it's changing x squared, this will be d dt of average y. So ddt of average y, on average, I will average, so dv will have average 0. Even though it has something stochastic. This I will explain you in the next class, that fx dv equals to 0. Okay, very important. This will come in the next lecture. Okay, that's why I'll put it in green. Okay, for the next lecture. The only things that will survive when I do the average is this term and this term. So one gets something like the following. One gets minus 2 over tau r, this part minus 2 over tau r, x squared, the dt goes, squared, plus that thing, which is 2d. And this is a very simple equation. Okay? It's a very simple equation because you have this, you can solve. ddt of something is minus a constant of the same, this thing, plus something else to be. And what you can see is that this I will emphasize in the next class. You can get x squared infinite times in the stationary limit, and this is, I'll come back to this, okay? This is kVt divided by kappa. This is the long time limit. So, in the long time limit, this width will be kVt divided by kappa. So the more temperature, the more fluctuations. But I will come back into this and try to clarify it better in the next class. Okay? Any questions? Okay, what you have to keep in mind from this second part of the lecture is what is the Langevin equation? What does it mean? Where do each of the terms come from? What is the overdamp limit? And the particular case of an overdamp Langevin equation, which is the Austin-Uhlenbeck process. Okay? Austin-Uhlenbeck is a spring with friction in a thermal bath. Here, color spring with friction, zero mass. In a thermal bath. Right? Okay, so if there are no more questions, I'll finish here. And next week I bring you homework about the first part, and I will also finish the lectures on the second part. So maybe we start with the applications of stochastic process in biophysics. If there are no questions, we go to a Q&A, we have to discuss, because this part has been very mathematical, but also it will be extremely important for the next of the course, because I will formulate a lot of biological processes with this mathematics. Okay, this will be the usefulness of this course. Right. So we see again Tuesday or Wednesday. We have to check the calendar.